Good morning, physics. Happy Monday. Today we were talking about our third and final law of Newton's, which is action and reaction. So here I have a very famous instrument called Newton's cradle that shows that for every action there's an opposite and equal reaction. Forces and interactions. Simply put, a force is a push or a pull. Force is not a thing, however, it is a mutual interaction between one object and another. For example, when you drive a nail into a board, does it automatically just sink all the way in? Unless you're Macho Man Randy Savage, probably not. This is because that nail is pushing up against the hammer. It's resisting going in. So Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. So every time you have a force, you have an equal and opposite force pushing against it. One force is called the action force and the other is called the reaction force. Either force can be the action or the reaction. The important thing to know is that they're parts of the same reaction. They're an interaction. So one time it might be, you say the nail is the reaction force and the hammer is the action force. That's what it looks like, but you could make an argument the other way as well. Once again, if I'm going too fast for you guys, go ahead and have the sub pause the video, and then we'll go from there. Two forces are equal. The reaction and action force are of the same strength, but they happen in the opposite direction. When you walk, you push down on the earth, and it pushes back on you with the same amount of force. Now what happens if you're walking on ice, though? You might not have enough friction to walk, so you can't get that equal force off the ground to propel you forward. You can't push down the earth as well because you have that friction that's making you slide. Identifying action and reaction. It's not always easy to determine which force is which. For example, what about a falling boulder? Is it gravity the action force? What's the reaction force? Is it the weight of the boulder? But weight is a force of gravity. So you see where it kind of gets a little tricky. Because it's gravity, there's obviously something acting on this rock that's falling. We can go backwards and say, well, maybe somebody pushed it, but that's not what we're talking about. We're talking about just falling. So an easy way to think about this, guys, is object A exerts a force on object B. Example, the earth attracts the boulder with gravity. And then object B exerts a force on object A, which is the boulder also attracts the earth with equal gravity. That boulder is pulling on the earth at 9.8 meters per second squared, and the earth is pulling on that boulder 9.8 meters per second squared. Just in opposite directions. Action and reaction on different masses. The force the boulder and the earth exert on each other in that last example is equal. However, the earth doesn't move as much as the boulder does. It doesn't rise up to meet that boulder. But then again, the earth is very, very big. It has a lot more mass. So it needs to accelerate a tiny bit to have the same amount of force. Think of it as mass times acceleration of the boulder equals the force of gravity, which equals the mass times the acceleration of the earth. They're all equal. The boulder has to accelerate a lot faster because it's smaller, but because it's smaller, it can accelerate a lot faster. Force and mass. A force exerted on a small mass produces a larger acceleration than the force exerted on a large mass. Example, rifle recoiling from shooting a bullet. Both the rifle and the bullet receive the same amount of force. The bullet launches while the gun barely recoils. Of course, if you have a bigger gun, you have bigger recoil because you have a bigger force. And inversely, a faster bullet. Misconceptions of action and reaction. What propels a rocket? If you said the impact of exhaust gases against the atmosphere, you're wrong. The rocket and a gun react because of the force they create. Air is not required. You can still have rockets where you don't have atmosphere in space. And they actually work better because they don't have that air resistance anymore. They don't have that drag. Newton's third law in helicopters, airplanes, birds, anything that flies. Helicopters is just the coolest example. The whirling blades on a helicopter, they actually work because they're pushing down, pushing air down. And it's not that they're pushing air against the ground, it's that they're pushing air down that they can lift up, because the opposite force is that their blades are going to go up. When lift equals weight, so the force of gravity pulling down equals the lift, an airborne vehicle, helicopter, plane hovers. They don't change altitude. But when lift is greater than the weight, an airborne vehicle rises. That's what airplanes are built to maximize the lift, so that they can get that air pushing down as hard as they can to push them up as hard as they can. Do action and reaction forces cancel? Since they're equal and opposite forces, why don't they just cancel to zero? Imagine, for example, this horse pulling a cart. As he's pulling the cart's pulling him, right? But this cart is something we call a system. This horse is pulling the weight of the cart, but the wheels decrease the friction. So even though it's pulling back on him with equal response, it can't get as good of a grip. It's not pulling, it's pushing as hard on the earth, so the forward motion is forward. The net force is forward. So as you can see here, this force of ground is bigger than the force of friction, and that's what allows it. Because these forces are equal, the force of horse and the force of cart. And that, to a little extent, this force of friction is pulling back, but not enough. There's more action going forward. That horse is pushing off of the ground, which is pushing it back harder than the cart is. Action equals reaction. If you were to punch a wall and hurt your hand, you could theoretically say the wall punched you. How hard does the wall punch you? Just as much force as you put in. If you put in 200 newtons of force, the wall is going to give you back 200 newtons of force. Now hold up a piece of paper. And you guys could do this after this lecture, but you could say that a heavyweight boxer couldn't hit this piece of paper with 200 newtons of force. You're correct, because the paper cannot exert 200 newtons of force back to the heavyweight. It would rip, tear, move. But if you were to place this paper up against a wall and give it 200 newtons of force, it could very easily return the favor. All right, so that's all of Newton's laws. There's no new equation for you guys on this one. Just remember the force equals mass times acceleration, and everything else that you've learned for Newton's law. There's a review assignment. You guys need to do the assignment. Remember, you can take a note card onto the quiz, so make sure you take a good note card. We're doing all 3 chapters, chapters 4, 5, and 6 on the quiz. Have a wonderful rest of your day, and I'll see you guys on Wednesday.